Hello everyone. This video is about improper integrals and how we use improper integrals to find areas or volumes or surface areas of regions that are infinite. The integrals we have studied so far represents areas of bounded regions. However, areas of unbounded regions also arise in applications and are represented by improper integrals. So if you look at the region that I have on the screen, that is a graph of y equals e to the negative x over 2 in just the first quadrant. Now, as you can see, that graph is going to go on forever. And what we want to do is find the area of that region. You might think this region has an infinite area, but as we will soon find out, it truly does have a finite area. So the first thing we have to do is to find the area from 0 to b, which is just going to be a general x value to the right of 0. And then once we find that, we will find the limit as b approaches infinity. So the very beginning part of this process is no different than what we've done in the past. So if we go to integrate this integral here, we're going to use u substitution, and I didn't show the steps, so if you want to pause and make sure that you understand how to get from the first step to the second, please do so. But after I get an antiderivative, it's right here. And then we're going to stick 0 and b into x, subtract the 2 to get our answer. And when I do that, this is what I end up with. If I simplify that a bit, it will be negative 2e to the negative b over 2 plus 2. Alright, so now what we'll do is, remember, we didn't want the area from 0 to some x value. We wanted the integral from 0 to infinity. So what I'm going to do now is, to finish this off, I'll take a limit as b approaches infinity. And I'm going to try and rewrite this. It'll be negative 2 over e to the b over 2 plus 2. And as b gets very, very large in this term, that denominator is going to grow and grow and grow. And so we're going to get 0 there for the limit. So our final answer will be 2, which means that this picture right here, shown on the right here, this picture, all of this area, all the way to infinity, has an area of 2 units. Okay, let's try another example. If I were to give you, if I were to give you an integral that looked like this, let's go from 1 to infinity of dx over x. Now again, that's an improper integral, so we're just going to rewrite that as 1 to b of dx over x. If I evaluate that integral, I will get the natural log of x, and I'll evaluate that from 1 to b. So now what we will have is the natural log of b minus the natural log of 1, or just the natural log of b. So what I'm going to do at this point is take the limit as b approaches infinity of the natural log of b. Well, to evaluate that, we're going to have to remember what the natural log graph looks like. And that kind of looks like this. So as we see, as we get larger in the x direction, the graph just continues to get larger also. So this is going to end up being infinity. In other words, this integral diverges. It does not have an answer, so we'll say it's a divergent integral. All right, so we're going to try one that's a little bit more difficult this time. We are going to integrate, I always do that, we're going to integrate kind of a double improper integral. So if we integrate from negative infinity to infinity, e to the x dx. So what we're going to have to do on this one is we're going to have to pick a convenient stopping point, which I'm just going to pick 0, but it wouldn't matter what point you picked. I just think that 0 is going to be more convenient. So I'm going to rewrite that as the integral from negative infinity to 0 of e to the x dx plus the integral from 0 to infinity of e to the x dx. So we'll do the same thing we did in the previous two. We're going to just go from b to 0, and then here we'll go from 0, we'll call this c, just so that it's something different, of e to the x dx. All right, so if I integrate e to the x dx, I just get e to the x. And I have to evaluate that from b to 0. And over here, the same thing. I'll get e to the x, and I'll go from 0 to c. So this one here is going to be e to the 0 minus e to the b power. And then I'm going to have to take a limit as b approaches negative infinity. Well, if I do that, I'm going to get 1 minus, and then what happens as b gets very large and negative? Well, if it's negative, I can write it as this, and then if it's very large, it's going to be 1 divided by a very large number, which will just give me 1. What about the second one, though? On this one here, I'm going to get e to the c minus e to the 0. And then I'm going to have to take a limit as c approaches infinity. And as c approaches infinity right here, that's going to also approach infinity. So the second half of this integral is going to be infinity. So we will get 1 from the first part plus infinity, which tells me that this integral is divergent. Sometimes improper integrals aren't as obvious. Here's an example of one that, if you just look at it quickly, it doesn't look improper, but it is. And that would be one that looks like this if I integrate from 0 to 1 of dx over the square root of 1 minus x squared. That is an improper integral because at one of the endpoints or somewhere in between, this function that I'm trying to integrate is undefined. I cannot plug 1 into x because if I do, I will have an undefined integrand. So what we're going to have to do is change this up a bit and go from 0 to b. And then if I do the antiderivative of that, it's arc sine x evaluated from 0 to b, which is going to be the arcsine of B minus the arcsine of 0. Now remember, the arcsine is just asking at what value, right here it's asking at what value is the sine 0, and the sine is 0 at 0. So now we have the arcsine of B minus 0. So to finish off this improper integral, we're going to have to take the limit as B approaches 1. And technically it's 1 on the left because we're going from 0 to 1. But either way, we're going to come up with the same answer. But we're going to get the arcsine of B. And as B approaches 1, we're being asked the question, where is the arcsine? Where is the sine value 1? And the sine has a value of 1 at pi over 2. So since we end up with an answer, we can say this converges. And the answer is pi over 2. Okay, I'm going to put one more on here. And there we go again. All right, so this one will be a little bit harder, a little bit longer, but we're going to integrate from 0 to infinity of 2 over x squared plus 4x plus 3 dx. So hopefully you guys recognize this as a partial fractions integrand. So we're going to work through it as a partial fractions. So to start, we're going to let 2 over x squared plus 4x plus 3 equal a over x plus 1 and b over x plus 3. So if we go through and solve that, we should come up with, let's see if I can find it, 1 over x plus 1 minus 1 over x plus 3. So that's what we're going to end up integrating. And instead of going from 0 to infinity, I'm going to go from 0 to b. So we're going to get the natural log of x plus 1 minus the natural log of x plus 3. We're going to stick in b and 0. If I stick in 0, I'm going to get the natural log of 1, which is 0, and the natural log of 3. So now the last thing to do on this problem is to take a limit as b approaches infinity. So as b gets very large, in fact, I'm going to rewrite this, I think. I'm going to rewrite this as the natural log of b plus 1 over b plus 3 minus, actually that's going to be plus natural log of 3. So I'm going to let you guys figure out what happens when we stick infinity in for b. What happens as b approaches infinity in that first in that first term there. So is this integral convergent or divergent?